Hi everybody. So today we're going to kind of continue our discussion related to data collection, and we're going to go backwards. So last lecture we talked a lot about sampling, potential biases that could occur, sampling techniques and methods. Now we're going to go one step back to the actual design of the experiment, and we're going to discuss some standards and approaches there, and then move on to the analysis, which happens at the end of the sampling process, and a couple of the common analytical errors that people make. So as far as the agenda for today, we'll discuss different types of experiments and key principles in designing those experiments. We're going to do a couple of examples to practice what we learned last class, and we'll cover in this lecture about identifying bias, because as I mentioned before, there's a lot of different types of bias, and there's no exhaustive list of the types of bias you might encounter, so it really helps to practice identifying potential areas that could introduce bias. And then, as I mentioned earlier, we'll get into a couple more common analytical errors when people do reach the analysis phase at the end of that research process. So first, I want you to take a minute and think about these two concepts, experiments and observational studies. Try to intuit what the difference is, and then we'll go through some examples and figure out whether they fall into an experiment or an observational study. So as some of you may have guessed, based on the words, the difference is pretty intuitive. Experiments are conducted where a treatment is applied to one group, to some groups, and different treatments or no treatment, also sometimes referred to as a placebo, is applied to other groups, and we take note of the differences in the form of effect size. Whereas an observational study can happen after the fact or during, but there's no actual experimentation taking place. You're collecting data that already exists through various methods. And that's all I'll say about it for now. I think, when we go through the examples, it'll become more clear, and I don't want to give away too much. So thinking about drug trials, would that be an experiment or an observational study? And it pretty clearly falls into an experiment, right? Drug trials, you have a treatment being applied. The data collection process tends to be more intensive, which is the case with experiments. And when you reach the analytical phase, you do that by comparing the differences between groups. Surveys, on the other hand, fall into an observational study because you're collecting data, and it can be somewhat intensive to collect that data, but you're not actually applying any experiment to generate that data, right? The data already exists. It's just a matter of you gathering it. Educational interventions might sound a little vague. I'll just give you a brief example. I took a couple years to do a Teach for America type program, and we used a new software and system for teaching, and the principal wanted to compare how that intervention, whether that intervention was more beneficial for students than traditional teaching methods. So this is similar to a drug trial in that you're comparing the outcome of different treatments applied to different groups. And it is, if you said it was an experiment, you're correct in that you're spending a lot more time setting up the processes for data collection prior to conducting your analysis. So let's go over types of experiments real quick. So the first one I want to talk about is randomized controlled trials. I put this in golds because I have a friend who works at nonprofit Give Directly, which you may have heard of, that refers to these as the gold standard. And he's a strong advocate in why would you do anything else. So they've done 20 plus randomized controlled trials on their nonprofit interventions to evaluate them, and he encourages other nonprofits to do the same. And I think there is a strong point that he's trying to make. Not everybody thinks of RCTs. Their randomized controlled trials can also be referred to as RCTs as the gold standard, but they certainly are in some cases, like medicine. So before medicine is approved for treatment by the FDA, it goes through a very rigorous process with strict standards, including a randomized controlled trial in which one group is given the medicine that's being trialed, and another group is given the standard of care or a placebo, and the effect is the differences in outcomes between the two groups is compared and shown to be statistically significant. So this is, in that context, the gold standard, and intuitively you can kind of see why. There's a lot of benefit to this approach. It helps first of all, there's the randomized component of it, where people are randomly assigned, which, as we talked about earlier, is a principle in design that helps to assure that the samples are both representative of the population, or all representative, because there could be multiple groups within the study. That said, randomization isn't perfect, and you could wind up with one group that is not representative. However, these are typically also controlled in the sense that the way the treatment is applied, and there are steps taken to ensure that the groups within the trial look similar to each other in addition to looking similar to the population. So recruiting participants for a clinical trial would include, sometimes includes, outreach to minority groups that might be harder to include in your trial through pure randomization, just because they're a smaller proportion of the population. So I pose this question to you: if randomized controlled trials are the gold standard in drug approval, and, as my friend says, should be the gold standard in evaluating nonprofits, why do we do other types of experiments? So take a minute to think about that. So the reason we do other types of experiments is it's not always possible to do a randomized controlled trial, and that's what these latter two bullets are trying are cases that you might address. So, for example, if you want to study the effects of a certain disease, you can't randomly assign people into groups that have the disease and don't have the disease, right? You can recruit participants, and then based on whether or not they have the disease, they'll be assigned to the appropriate group. But you can't randomly assign them to groups because, they have the disease before the fact of the analysis, or don't. Similarly, case control is also after the fact, in that I'll share with you the example I learned when we were studying case control studies. So in this case, the example I was given is you're at some kind of a resort and there's been an outbreak of a disease, and they want to identify the source of that outbreak. And in doing so, they look at people who had, I think it was a hamburger from the resort, and they compare the proportion of people who had the hamburger and the disease with the proportion of people who did not eat the hamburger and still wound up with the disease. So again, these are just different designs of studies or experiments that are sometimes necessary because you can't always meet the strict requirements of an RCT. So these are not different types of experiments. These can be applied to any situation in which an experiment is occurring, but these are some principles to be aware of when you're designing your experiment. So single or double blind is what it sounds like. it means that in the case of double blind, both the participant and the researcher or experimenter is not aware of which subjects fall into which group. So if we go back to the example of drug approval, they don't know who's receiving what form of care. Both the participant is unaware and the researcher is unaware. If only one of those two are unaware, we say single blind instead of double blind. And that helps to avoid certain kinds of bias. You could imagine there's such thing as the placebo effect, where people believe they're receiving a treatment and see some kind of improvement just as a result of the power of belief. Similarly, knowing the type of treatment, the researcher knowing the type of treatment that a subject is receiving could influence their measurements in terms of evaluating the outcome of that treatment based on their expectations. So this is why we try to apply the principle of being double blind to most experiments when possible, and if not possible, at least single blind. These other two principles are really important, and the benefit that I list for each of them does apply to both, but I think it applies more to the principle I listed it next to. So in the case of repetition, this really just means recruiting more subjects, having a larger sample size, and repeating the experimental process over and over on many units. So this will improve the accuracy of your measurements. Not of your measurements, of your estimates of effect size. As this is a key principle behind statistics, is as you collect more data, you get closer and closer to the truth, right? And there's a few theorems and principles that we've studied that shine more light on that, but this is the idea behind the principle of repetition. Is you increase your sample size, your statistic will be more accurate, the band of uncertainty associated with your statistic will decrease. Replication, on the other hand, sounds similar, but is different in that you're not recruiting more participants, you're not collecting more data, you're simply measuring that unit of the experiment multiple times. So the key benefit here is to reduce the variability in your measurement. There is such thing as measurement error, depending on the type of experiment. And the more times you measure an experimental unit, the more you reduce that variability. It does also improve the accuracy of your statistics, but the main benefit of replication is reducing the variability in your measurements. Okay, so let's talk about some examples of bias. We covered this last lecture, but I want to go over different types of bias. I mentioned one at the end that's not statistical, but it does relate, and I'll talk more about why later. So the first type of bias I want to share a story about is the caveman effect. So, when we talk about Neanderthals, we associate them with living in caves. And the reason for that is actually really arbitrary. It's because a lot of the data and information we have on them are from paintings that were in caves. They very well might have lived outside of caves and made paintings and drawings and left artifacts on trees or, out in other areas of Earth, but those were likely washed away and lost to time, whereas inside of a cave, the paintings were well preserved and we were able to study, fossils, remains, and artwork that they left behind. And that's a bias that still exists today. We don't actually know how they lived or where they spent the majority of their time, but the evidence that we have of them that remains is mostly from caves, and so they're referred to as cavemen. Another type of bias that I think we encounter a lot is survivorship bias, and that's what the image to the right is about. So I'm just going to pose to you the research that led to this image. So the military wanted to improve the efficacy of planes, and they hired statisticians to do this. And they said, look, here's a bunch of planes that have come back from war with damage, and they plotted all of the damage as you see in this image. What can we do to improve the durability of these planes? And I want you to think what sort of bias might be an issue. And I think that the word that I'm introducing here, survivorship, is a big hint. So I want you to think about that for a minute, and then I'll let you know. So some people are going to look at this image and say, well, let's just add reinforced metal to these areas, the tips of the wings, the center around the cockpit, and the tail, because that's where most of the bullets seem to be hitting. However, these planes made it back from war, meaning that the damage wasn't substantial enough to put the plane out of commission. So this is what we're talking about when we say survivorship bias. There are likely planes that sustained injuries in this area as well, and those injuries may have been more significant to the point that they didn't make it back, they did not survive, and that's where the reinforced material needs to go. And a statistician did realize that, and that's why we have this image today. It's a very famous case of survivorship bias. So this is one example of looking for bias that, at the time at least, was not readily apparent, did not have a name, and performing the correct analysis by identifying issues with the proposed analysis. Lastly, I wanted to talk a little bit about sunk cost bias. This is not a statistical type of bias. You may have heard of it before. The idea is that somebody sinks some money into an idea, and because they've invested some amount of money, time, effort, they are reluctant to abandon that theory, and more likely to continue to sink time, money, and effort, even as it proves to be more and more fruitless. So this is not statistical, but I wanted to bring it up in the sense that as a researcher, there can be types of sunk cost bias. So you might have a theory as to your research question, and you're invested in proving that theory or point with your research question. But as you collect your data and you form your analysis, you get results that contradict your theory. And it's important as a researcher to remain objective and say, well, it could be the case that my theory is not valid. This is not what I intended to see. It's a little counterintuitive. Maybe you test the data more as a result, but you need to be prepared to accept whatever the data is telling you. And that finding is in and of itself a finding. That could be useful information for future research. It could be that the results are inconclusive and more research needs to be determined, but it's important to avoid this kind of error in thinking where we have a bias, which is natural, and we need to be aware of that in the way we're thinking about the research question and what we expect to see from the data. And we need to be flexible and open-minded enough to accept when the data is telling a different story. So let's do some practice questions identifying types of bias. So these are just two examples I came up with. Gallup and Rasmussen are both famous pollsters in the States. So let's start with the first example. Gallup wants to learn about U.S. sentiment on the war in Gaza, so they conduct a telephone survey. I want you to think proactively about what type of bias they may be introducing with their approach. Yeah, so in this case, the information about the war in Gaza is a little bit of a red herring. That's not where the bias is introduced. The bias is actually introduced through the telephone survey. Not everybody has access to telephones. Not everybody who's willing to answer a number from an unknown call. Not everybody is willing to answer a number from an unknown call. So there is some reason to believe that there's some selection bias here. While most everybody has a cell phone at this point in time, there are certainly people who don't, and it could be the case that their sentiment on political issues is different than people who do. In addition, we talked about how not everybody's going to answer the telephone or be willing to spend time responding to the survey. So here's an example that's more specific to you guys. So Rasmussen is curious about what people in Blacksburg think of the idea of opening a Walmart in town. So they send out a survey. They include return postage, so there's no cost to send it back, and they mail it to every resident in town. Take a minute, and there's a few types of bias that come to my mind here, and I'm curious to hear what you think. And if you think of something that I didn't even mention, please leave it in the comments for other people to see and review. So in this case, there's what the immediate bias that comes to mind is a response bias, or what's known as a response bias. And we talked about this last lecture, right? Filling out a survey in the mail takes time, and not everybody feels strongly enough about an issue to fill out the survey. Similarly, even if people feel strongly, they might not believe that filling out the survey is going to have much of an influence or is worth the effort to do so. So there's definitely a response bias there. There's also a little bit of a selection bias, right? If you're mailing it to every residence in town, what about residences with multiple people living there? What about people who own multiple residences, right? So it's not quite representative of the entire population of Blacksburg. So those are a couple biases that come to mind. Like I said, there are definitely more. As we talked about in the survivorship example, sometimes there are biases that have yet to have a name or that we haven't thought about yet. If you came up with some in doing these examples that I didn't mention, like I said, please leave them in the comments. This is just meant to exercise this new way of thinking, of recognizing biases in your studies before conducting the analysis. All right, so I want to talk about a little bit about lurking variables. Now, we talked, the first half of this lecture was really about experimental design principles. Now we're going to talk about errors in the actual analysis. So here's kind of a silly example to illustrate the point of a lurking variable, which you can see here in this picture. Is the idea of a lurking variable is it has an effect on both the response, also known as the dependent variable, and the independent or explanatory variable. So because it affects both of these things, right, we never say that there's a causation between the explanatory variable and the response variable, because it could be the case that there's a lurking variable that actually causes the response variable more so, and is correlated with the explanatory variable. All you really say when you conduct this bivariate analysis is there's a relationship, and as these things co-occur, these are the effects that we see. So let's go over kind of a silly example. This is a true statistic. Countries with more TVs per household have a higher life expectancy. So the mistake in inference would be to say that causally TVs increase your life expectancy, right? Scientifically, it's kind of a ridiculous idea. Like, on what basis do we think that TVs would improve your life expectancy? I want you to take a minute and think about what the lurking variable there might be. So the lurking variable here is hopefully pretty obvious. It's related to economic development or household income, or just as a whole how the country is doing in terms of standard of living. And countries with more GDP and per capita are more likely to have a TV, more likely to also have better hospitals and healthcare resources available. So I think that's causally more likely to be the explanatory variable, or the causal relationship, than TVs improving life expectancy. Another example, which unfortunately comes up quite a bit still, and this is related how people can mislead you with statistics, is disproportionality in crime statistics. So people will unfortunately present data as to certain subgroups being more likely to commit crimes. And the response, which has been proven time and time again, and unfortunately still needs to be repeated to this, is there is a lurking variable when it comes to crime, and that is poverty. And we know that in most countries there is some amount of segregation when it comes to which groups of people live in high-income areas and low-income areas. And the lurking variable that really explains differences in crime statistics is income or poverty, and is not at all related to different subgroups are more violent or more likely to do this. But this is misinformation that unfortunately you do hear from time to time, and so I wanted to point that out. I think that's a good canonical example of a lurking variable. All right, so the last thing I want to talk about is confounding factors. These are different than lurking variables, but it's another mistake you can make. Ignore the image on the bottom for now. We'll get to that. But these really result from incomplete blocking or stratification, or from lack of randomization, or you did randomize, but you didn't have enough data for that randomization to be representative of your population. So if you apply those principles, this is unlikely to happen. But just like we have other types of studies besides RCTs, it's not always possible to apply these principles in every way. And I'll give you an example involving agriculture. So statistics actually got its start studying different types of agricultural interventions. Those many early statistical applications had to do with agricultural experimentation. And so people would vary like the fertilizer used. And one way to do that is to split the field in half, right? So you apply fertilizer A on one half of the field and fertilizer B on the other half, and then see what the yield is like between the two different halves and compare those statistics. However, it could be the case that there's a confounding factor. It could be the case that one half of the field gets more sunlight than the other half of the field. So we can't say definitively that the fertilizer was better. It could be that the level of sunlight is actually what's causing the yield, is actually influencing the yield more than the type of fertilizer. So one way to fix that is to cut the field into many pieces. So you're sort of randomizing how much sun is in each piece and apply the different fertilizers to each piece randomly or in a stratified or systematic way like we talked about last lecture. So that's one example of a confounding factor. Another way to address confounding factors, as I mentioned here, is through blocking or stratification. So let's say, we'll use the example of drug approval. There's an anxiety drug that's been developed, and we want to test how it affects the study habits of students. Well, there's different types of anxiety, and maybe there's reason to believe that people with generalized anxiety disorder will have a different effect than people with obsessive compulsive disorder. So we block those people into two distinct subgroups, and we randomly pick people from each and assign them to either take the placebo or the new drug that's been developed, and then compare the study habits either within the two groups or across the two groups to see if they're different. And hopefully we're applying principles like double blind and obviously this is an RCT like we talked about before, but we are blocking for the type of anxiety people have because we believe this could be a confounding factor. It might not be. It could be that the medicine affects people with generalized anxiety disorder in the same way it affects people with obsessive compulsive disorder. But the only way to measure that and evaluate that is by using blocks or strata to separate people into other groups. Okay, so thank you guys again for your time. This was another shorter lecture. Hopefully this change of pace from the more mathematical concept to the study design and sampling concept has been helpful, and we'll continue to discuss some of these principles as we move on to inference in coming lectures.